Hello. Hello. Let me do all this stuff. In my video. Turn on the chat. Give you guys the usual links. In non-math related happenings in my house, today is my wedding anniversary. I'm married for 13 years, so it's not particularly exciting, but it is news. There are the usual links. There's the attendance and the tutoring and the spring quarter evaluation. Hopefully you guys have all done all those things. Thank you, Teresa. Appreciate it. Let's see. What? I was looking over here. Just looking at Rodmacher's homework. That's, I didn't see when it's due. June 4th. Okay, we could probably go over some of that if you guys wanted to. Oh, also, actually, before we get going, I do want to say for those of you in Carlson's class, Grant shared with me a handout that he made on the walks, and I forgot the other thing is. Let me share my screen with you guys. It's on Canvas. It's in the modules. If you look for those in Carlson's class, if you look in the modules, at the bottom under the useful handouts, you will see the multinomial coefficient and counting walks on a graph. And that has a handout that Grant wrote up that has kind of stuff explaining how that works. So if that applies to you, I mean, the multinomial coefficient stuff is stuff we can probably all talk about, I guess, but the walk stuff seems a little bit out there. So he writes a whole bunch of stuff down. So if you have questions about that, you can look there and get some help with that. It's helpful. So yeah, and then yeah, walks, all that kind of stuff. For those of you not in Carlson's class, don't look at the walk stuff. It's definitely not anything anyone should be asking you about. So yeah. Was I sharing my screen? Did I stop sharing my screen? Okay, I guess that's weird. I don't know how I guess I accidentally clicked the stop sharing button on purpose. I had a couple double integral examples in mind, if that's something you guys still want to see. Okay, awesome. Let's start there. And then if any people have questions about Rodmacher's homework, sorry, where'd you go, Rodmacher's homework? Yeah, we can even do one of the, yeah, there's a double integral there. There's a couple double integrals. They seem pretty straightforward, but we can definitely look at a couple of those. In fact, actually, let's look at a problem similar to problem 2, slightly different. So his problem 2 says, where'd you go, Patton? Says, find the volume of the region bounded above by the surface. I'm going to change the surface. I'm going to change it just a little bit. Z equal to, yeah, let's make it x e to the xy, and below by the square. So above by this, below by, let's say, the rectangle, given by x is between -2 and 1, and y is between 0 and 4. Really, rectangle, square, it's right, either way is going to be fine setting this up. So if I was trying to find the volume, right, that's bounded above by this and below by this region, I'm really just setting up a double integral of this surface, x e to the xy, over these limits of integration. Now, the question you want to answer before you do anything else is, what variable is going to be easier to integrate with respect to first? Is it easier to integrate with respect to x, or is it easier to integrate with respect to y? And I think it's definitely y in this case, right? Because x, if I pretend, like, if I think of y, like if I think of this as a 2 for a second, x e to the 2x, that's going to require integration by parts. Whereas 2e to the 2y is just going to be a straightforward antiderivative. So I would definitely do it with respect to y first. Which means the y limit should be the inner limits. and the x limit should be the outer limits. You could certainly set it up the other way, but it would be more work to do it that way. Another thing to be aware of though is sometimes, right, if you do set it up one way and after you do the first integration, the second one looks like something is awful, you can always go back and do it the other way. So doing it this way, here's what we're going to get. So the integral of x e to the xy with respect to y is x e to the xy divided by x. Here, if you're having trouble seeing that, here's how I encourage you to think of it. The integral of 2e to the 2y with respect to y would just be 2e to the 2y divided by 2. Right, because the derivative of this with respect to y is just that. In the same way here, after these x's cancel, the derivative of e to the xy with respect to y is just e to the xy times the derivative of xy, which is x. So it totally works out nicely, as I'm sure was intended. Cancel these and plug in the 4 and the 0 for y. So you get the integral from -2 to 1 of e to the 4 times x minus e to the 0 times x e to the 0, which is 1. And then we're going to do the same sort of thing. So we're going to integrate. I wish this glare to go away. One sec. Sorry, let me make this screen bigger so it covers up all the gray parts. There we go. Great. Kind of great, I guess. Okay. Anyway, integrating this, we're going to get e to the 4x divided by 4 minus x from -2 to 1. And here's where my numbers probably aren't very nice. We're going to get e to the 4th over 4 minus 1 minus e to the -8 over 4 minus 2. And you could probably simplify that a little bit more, but that's about all we really want to do with that. So definitely with this problem, the one he's written you, it is important to consider the order you want to integrate with it first and second. And definitely there is you could do this the other way, but it would be worse. It would still work out eventually, but it wouldn't be nice. Okay. Look back on that for a second. Sure. Okay. All right. So let's look at, where'd you go? Yeah, thank you. Let's look at this one. Sorry, one sec. Okay. So think of this double integral. The integral from 0 to 1, and then the integral from 0 to y, from the square root of 1 minus x squared, dx dy. I'll say about this first is if you happen to take Dr. Dedell for 17b, you would probably know how to do this integral because it's a trig substitution. I imagine most of you don't know how to do this, which is perfectly fine. You shouldn't really know how to do this in this class. If there is a way of doing this, you let x equal sine of theta. It's kind of neat, but it's not that important. So the way you should do this, if you see something that looks like you don't know how to integrate it, the usual go-to is I should probably change the order of integration. And usually that means drawing the region. And so in this case, I've got to draw my region. I'm always looking at the inner one first. So this is x equals 0 to x equals y. Here's x equals 0. Here's x equals y. So right, I'm going from as far left as here to as far right as there. And then these little strips or arrows, whatever you want to call them, are going as low as y equals 0, which is right here, to as high as y equals 1, which is up here. So there's the region we're looking at that we're going to switch. So now we're going to use vertical arrows or strips, or whatever you want to call them. And we can see that, so our lower bound is going to be y equals x, and our upper bound is going to be y equals 1. And then our arrows are going to go as far left and right as x equals 0 and x equals, that's also going to be 1.11. So our new integral is going to look like, we're going to go as far left as x equals 0, as far right as x equals 1. We're going to go as low as y equals x, as high as y equals 1. Same function. Now we're changing the order. So that's how we do that one, or that's how we would change that one. And then we have to do it. A lot of the time after you change it, you end up getting something that's going to turn into a nice U substitution. Ooh, 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 ooh. So I'm saying a lot of oohs here for a reason. Yeah. So the problem here, the problem with this problem that I made up, sorry. So here's the problem, is that when you integrate this, you're going to get the following. You're going to get a y times the square root of 1 minus x squared. And when you plug in x, that's going to be fine, because x times the square root of 1 minus x squared will lend itself to a straightforward u sub. When you plug in 1, it's not going to be fine. So I made up a not great problem. So I can fix it, but I'm going to need a new page. So here's the problem we actually should have done. Sorry. No. Yeah. I think it's a pretty easy change. Yeah, I just want to go from x equals y to x equals 1. Yeah, okay. Sorry, sometimes you try and change things up so they look good, but you don't. So we're really going. Sorry, that's what it actually should have been. So this one turns out okay. So it's still the same first step of rewriting it. Well, it's slightly the same, but it's a little bit different because our region is a little bit changed now. So now our region, we're going as, yeah. Sorry, I got myself. So x equals y, that's our left boundary, and x equals 1, that's our right boundary. Sorry, we're doing this. There's our left, there's our right. And then the y values go as low as y equals 0 to as high as y equals 1, which is exactly where they intersect. So then we're going to change it. The vertical arrows are vertical strips that go as low as y equals 0 and as high as y equals x. And go as far left as x equals 0 and as far right as x equals 1. So this one's going to be doable. This one's going to be the integral from outer limits are x equals 0 to x equals 1. Inner limits are y equals 0 to y equals x. Sorry, my brain just, what is going on? Wow, I'm sorry, you guys. I just lost it completely. Did I make a mistake here? I'm going from x equals 1 to x equals 1. I feel like I have this wrong somehow. And I apologize. Yeah. Yeah, I do. Sorry, I have. Yeah, sorry, I have these wrong to start off with. Sorry, I think I confused myself by writing the x equals here. If we just write it with a y and the 1, it's more, at least to me, it's more obvious it should be dx first because these should always be the opposite variables. Sorry about that. So here's why I was getting caught up, because I saw that I was about to switch these and have dx here, but I just said we don't know how to integrate this. We don't. So sorry. They're supposed to switch this way. Right, that should be a dy because it's y equals yeah. Sorry, sometimes your brain makes tiny little mistakes like that. So then we can anti-differentiate this, and it works out nicely. We get y times the square root of 1 minus x squared from y equals 0 to y equals x. And then we can plug in the x and get the integral from 0 to 1 of x times the square root of 1 minus x squared. We can plug in the 0 and we get minus 0 times the square root of 1 minus x squared. And then we can do a u sub and let u equal 1 minus x squared. Du is negative 2x dx. So du over negative 2 is x dx. And never a good place to erase. Sorry. Let's go ahead and erase. Sure. So doing this, we end up with, so instead of x dx, we get negative du over 2, or negative 1/2 du, and that's taking care of the x and the dx. And the square root of 1 minus x squared becomes the square root of u. And if you're like me, I would like to change the limits of integration. So if x is 0, u is going to equal 1 minus 0. If x is 1, u is going to equal 1 minus 1. And specifically in this case, when I end up getting a negative and I end up getting the limits of integration out of the usual order, I would go ahead and change this to positive 1/2 the integral from 0 to 1 of the square root of u. Right? If you change the order, that changes the sign. And so since there's a negative here already to kind of account for that, it seems really nice just to make it like that. It's not necessary, but it does make it, I think, easier. So then we're going to integrate. We're going to get u to the 3/2 times 2/3 times 1/2 from 0 to 1. And then we're just going to plug in the 1. 1/2 times 2/3 is 1/3 times 1 minus 0. So we get 1/3. Oh. My lights just flickered. I think everything's all right. So the challenging part, the part that's hard about this when you do it the right way is the changing of the region of integration, right? That's usually going to be the challenging part about something like this. I think here. Sure, I've got one. Do I have one? Yeah. All right, let me make sure I don't screw this one up. I want to do I want to find the volume bounded above by z equal to the natural log of x. Yeah. And below by the region in the plane bounded by y equal to 2x and y equal to x squared. Yeah, that should work out good. Okay, yeah. So here's what we're looking at. We're definitely doing a double integral of the natural log of x. And then over this region. So we might want to draw this region. Here's y equals 2x. Here's y equals x squared. And this is the region in the xy plane that the surface, right, is like the bottom of like the, we've got kind of this deal, right? We've got, and then it's going up. And there's somewhere like, I don't know, something strange. Picture looks okay. I'm not too bad about that. That's kind of what we got going on. Something like that. We need to find how to describe this region. And so to me, at least, the easy way is just to do it in terms of the way the function's already given, right? I would definitely think of this like having little vertical strips. Say, okay, I'm going as low as y equals x squared to y equals 2x. And then I'm going from left to right, x equals 0 to x equals 2. And I know that because I've done this problem, or I've set this problem up before. But right, if you set 2x equal to x squared, you're going to get x equal to 0 and x equal to 2x. Sorry, x equal to 0 and x equal to 2. Now, why am I'm really like, for some reason, my brain is really struggling with making these the right way. So let me ask you guys, should this be dy dx or dx dy?
It would be dy dx because the inner bounds are from in terms of x or something, or?
I believe that is correct. Although my brain is really having a hard time making that feel right. But that is definitely correct. Which is too bad because it's not the way I wanted to turn out. Oh well. Okay. So let me change one tiny thing, which was not I'm going to change the surface. I'm going to change it to natural log of y. Because I want to make this a little more interesting. So to me, if either way I was given it, I would still set it up this way first because it just feels natural, right? They gave us the function as functions of x, so it seems reasonable. Like, yeah, I would definitely set it up this way. So the thing is, natural log of y is certainly something we can integrate, but it might not be the way I want to do it. So instead of doing the integral of natural log of y, although we could totally do that, and we might even do it just to kind of show both ways, I would probably default to doing it the other way, meaning I would probably take this region. There's y equals x squared. There's y equals 2x. And I would probably rewrite this as x equals y over 2. X equals the positive square root of y. And think of my strips being horizontal. So they're going as far left as x equal to y over 2, as far right as x equal to the square root of y, and then as far down as y equal to 0, and as far up as y equal to 4. Still the same function. Yeah, it's not going to be better. Oh well. And then you're going to have, instead of dy dx, you're going to have dx dy. That might be, we'll see. It might suck either way, to be really true. Might be awful both ways. Okay. At least the first step here doesn't seem too terrible. Right? Integrating natural log y with respect to x is just a straight shot x natural log of y. So we're going to get the integral from 0 to 4 of x natural log of y from y over 2 to the square root of y. This is not a terrible. This is a good problem. I could totally see someone asking a problem like this. It's not particularly nice, but it's not like super ugly. So then we're going to plug in each of our limits of integration. So we have the integral from 0 to 4 of the square root of y times the natural log of y minus y over 2 times the natural log of y. Now here is the gross part. For each of these, you would have to do integration by parts. They're not terrible though. They're one-step integration by parts. So let's write them down. So for this one, and again, you're always letting you, you know what? You could actually put it together. So you don't have, so what I'm saying is you could actually write it like this. And just do one integration by parts instead of doing it for each of them. It definitely, you can always do if you have a natural log of y times just power, or natural log of your variable times just powers of your variable, you can always do a one-step integration by parts. And it could be natural log of y, or natural log of y times y squared plus y cubed plus y, a bunch of different powers. You could combine them all into one thing instead of trying to do, like I was about to, two different integration by parts, which seems kind of terrible. So let's just do it as one. We're always going to let the u equal the natural log, except the first letter of late. And then the du is going to be 1 over y dy. The dv here is going to be kind of ugly. The dv is going to be all of this. So it's going to be y to the 1/2 minus y over 2 dy. And then the v is the antiderivative of this. It's going to be y to the 3/2 times 2/3 minus y squared over 4. Not particularly lovely. But when the v gets multiplied by the du, this 1 over y is going to distribute through and just change the power. So it's not going to be that bad. Okay. So we're going to end up getting, and so actually, so here's where I would probably do I would probably just write out the antiderivative instead of writing it out with the limits of integration. So I would say, okay, this is going to give me u times v, the natural log of y, times all of this, minus the integral of v du. So when I do that, it's not going to be pretty, right? It's 2/3 y to the 3/2 minus y squared over 4 times 1 over y dy, or dy over y if you're short on space. What's going to happen here is you're going to multiply the 1 over y by each thing, so you're going to get 2/3 y to the 1/2 minus y over 4. So that's what I get. I get natural log of y times 2/3 y to the 3/2 minus y squared over 4 minus the integral of 2/3 y to the 1/2 minus y over 4 dy. All right, it's divided each of those things by y. So here's what we're going to get. So I've got all of this, natural log of y times, gosh, I keep trying to write 2/3, writing a 3 on top, times 2/3 y to the 3/2 minus y squared over 4 minus, let's go ahead and integrate this. So the integral of 2/3 y to the 1/2 is 2/3 y to the 3/2 times another 2/3 divided by the 3/2 minus y squared over 8 from 0 to 4. Something that I've noticed over the years, specifically with these powers of your variable times natural log of y ones, when you do these, so you always have some dv, right? Which is powers of x, and you integrate it, and you get, y to the 1/2 integrates to this, y over 2 integrates to that. And then when you get to the integral of v du, you always get back to essentially the same integral, because you've taken the antiderivative, so you've added one to each of the powers, but then you've multiplied it by 1 over y, so you've taken away that one power you added. The coefficients are different, but you're essentially doing the same antiderivative that you did before, just with slightly different coefficients. So that always happens when you have a natural log times a power of your variable type of integration by parts. Okay, then the rest of this is just dumb. So, real dumb because I'm dumb. Yeah. So there's a small problem. And the problem is that the natural log of y is undefined at 0. So we could do, we're not going to do, we could do, what's it called? An improper integral here. Yeah, we're just going to leave it at that and say that's how you're going to differentiate that. And someone, so one thing I will say is, I definitely see professors accidentally make mistakes like this on exams where they didn't think about the fact that you were going to have something undefined. So if that happens to you, or like you're integrating something, you get to the end and it feels like you're plugging in 0 to a natural log or 0 to a 1 over a square root of something or whatever, you have kind of two avenues to pursue. One, you think the professor made a mistake, ask them. Two, you think it might be an improper integral and you're supposed to use a limit from the beginning. I would say this is definitely not the second type, right? Like if you saw that improper shouldn't be a double integral. So if you think it's improper, like that should only be a single integral. And I forget, we talked about improper, is improper integrals this order? No, I think I'm thinking of a different class as improper. You guys should have talked about improper integrals in 17b a little bit. Okay. Sorry, 16b we definitely not. All right, so yeah. Sometimes you come up with stuff and it doesn't work out. See if I can throw something else on here. I want to see. I guess you should ask before I just keep going. Are there any questions you guys have? I know I usually ask that at the beginning, but I didn't.
Could we go over a problem about independent probability?
Sure.
Thank you.
Okay, let's see here. Let's see, we have an Huh, interesting. So I'm looking at his earn problem. His earn problem is really just a card problem that he turned into earns because he's using 13 of 4 different, like it's definitely like it. So let's say an earn contains 10 red, 10 green, and 10 yellow balls. And we're going to draw without replacement. We want to find so first we're going to do a conditional probability. So what's the probability that the first ball is green given that the second ball is, let's do red. And then we'll see the difference between green and green and green and red. So what's probably the first ball is green given the second ball is red. So this actually requires, right, this is a tree problem, right? That's all. So when we're talking about conditional probabilities, it doesn't have to be a tree, but most of the time a tree is the easiest way to get there. So first ball, I have 3 different possibilities. It could be red, it could be green, or it could be yellow. And the second ball, again, 3 possibilities. Red, green, yellow. So it might actually could look better. Make it a little nicer. I forgot 3 different probabilities. Okay, so where'd you go? Right here. So in the beginning, each thing has a 1/3 probability of happening, right? Because there's an equal number, or I really say a 10 out of 30 probability of happening. So there's a 1/3 probability of red ball, 1/3, 1/3, green, yellow. But now the rest of these probabilities are going to be out of 29, right? So there's a 9 out of 29 probability of getting a red ball after first picking a red ball. There's a 10 out of 29 of getting a green, and a 10 out of 29 of getting a yellow. And not surprisingly, just like we see every time with the tree diagram, all of these things add up to 100% or 1. 9 29s plus 10 29s plus 10 29s is 1. Right, the same sort of thing down here. It's just that green is going to be the 9 29s one, and red and yellow will be 10 29s. Same deal down here, except now yellow is going to be 9 out of 29, and both red and green will be 10 out of 29. So the probability that the first ball is green, given that the second ball is red. Okay. So that's going to be the probability that the first ball is green and the second ball is red, divided by the probability that the second ball is red. Okay, so what's probably the first ball is green and the second ball is red? Well, that's going to be first ball green 1/3 times second ball red 10 29s. And I should point out, right, so the formula I'm using there is, right, this is really the formula where it's the probability that the first ball is green times the probability that the second ball is red, given that the first ball is green, right? Which is just this times this, which is what you always are getting when you're doing the tree diagram. You're always getting that. Probably that the first thing happened, and then probably if you're in that section, that the second thing happened, given that the first thing already happened. And then the denominator, probably the second ball is red, is going to be all the way to the walk and be red. So it's going to be 1/3 times 9 29ths plus 1/3 times 10 29ths plus 1/3 times 10/29. Now, if you notice all of this, the bottom just adds up to 1/3. Because it's 1/3 times, I can factor out the 1/3 and the rest of it adds up to 1. Nine 29ths plus 10 29ths plus 10 29ths is 29 29ths. So canceling the 1/3, I end up with 10 29ths over 1. So the probability that the first ball is green, given that the second ball is red, is 10 29ths. So now let me ask you a completely easier question. What's the probability that the first ball is green? It's not a trick question. It's 1/3. Yeah, exactly. So that tells me that these events are not independent, right? The first ball being green and the second ball being red, because knowing one of them affects the probability of the other. Right? For them to be independent, the probability the first ball is green and the probability the first ball is green. Oh, sorry. I might have said that slightly wrong. 1 second. I need to back it up. So no, I'm fine. Yeah, sorry. No, this is totally right. Yeah, that's right. Probably the first ball is green is 1/3. Probably the first ball is green, given the second ball is red is 10 29ths. So clearly these are different. They're dependent on each other. Knowing one affects the probability of the other. We could also use this sorry. I'm coming up with independence questions can always be challenging. So I want to know is the event that what am I trying to think of here? But that's dumb. Sure, but the first 2 balls are red. Is that independent? No, that's gonna be dumb, James. Can't think of a good question here. Okay, independent from the third ball being yellow. This might be too much. Yeah, that's too much. All right, let me back. Let me ask this kind of question instead. Let me ask. So we asked about different color balls, like knowing the second one is something and asking about the first one. What about the probability that the first ball is red, given that the second ball is red? And I do want to point out, this is definitely different than the probability that the second ball is red, given that the first ball is red. This second thing is much easier to calculate. Given the first ball is red, what's the probability the second ball is red? Well, it's 9 29ths, right? If you know the first ball is red, you took 1 red ball out, there's 9 red balls left out of 29 total. So this is pretty easily seen to be 9 29ths. This, on the other hand, we have to do the same sort of calculation for this. So this is going to be the probability that the first is red, and the second is red divided by the probability that the second is red. Yeah. So, yeah. So this top thing here, it probably is going to be similar, but not quite the same. Probably the first is red and the second is red is 1/3 times 9/29. Right? You're just trying to find the ways to get the red right. Which is slightly different than what we had for the previous one. So the previous one we had green red, and it was 1/3 times 10/29 because we hadn't taken a red ball on it. And probably the second ball is red should be the same probability as it was before, right? It should still end up being 1/3, which kind of makes sense if you think about it. If you think about, if you say not knowing anything about the first ball, what's the probability the second ball is red? Well, you can kind of pretend like you just don't know anything, and you're picking the second ball out of 30, and 10 out of 30 is still 1/3. And that usually works that way, where if you kind of pretend like the first thing didn't even happen, and you're just asking what's the probability that the second ball is red, you can just kind of be like, well, if it was 10 red balls out of 30 total balls, it would be 1/3, and it still works that way. It works that way with cards too. If you say like, what's the probability the second card's an ace, given that, or if I just say what's the probability the second card's an ace, it's still going to be 4 out of 52, regardless of what happened first. Right? If you don't know what happened first, I should say. If you know what happened first, then it's different. If you don't know what happened first, you can say, oh, the probability of the second card is just 4 out of 52. I can show you that in a second. It's the same as this, though, really. So this is going to be, so probably the second ball is red is 1/3 times 9/29 plus 1/3 times 10/29 plus 1/3 times 10/29. Again, that's just 1/3 times 9/29 plus 10/29 plus 10/29, which is just 1/3. And those cancel out. So interestingly, these end up being the same. Which I don't think always happens. It definitely doesn't always happen. In the same sort of way, you can talk about the probability that the second card is an ace is 452, because there's two things that can happen. The first card could be an ace or not, and it can be an ace with probability 4 out of 52, it cannot be an ace with probability 48 out of 52. And the second card can be an ace. Here it's probability 3 out of 51, or not an ace, 48 out of 51. Here it can be an ace with probability 4 out of 51, or not an ace with probability 47 out of 51. And if you add up all the ways to get to an ace for the second card, it's this times this, plus this times this. I feel like I've done something stupid here. No, I haven't. So if we add these together, well, I can factor out a 4 out of 51, right? We've got a 4 out of 51 times 3 out of 52 plus 4 out of 51 times 48 out of 52. Factor that out. We can also just multiply it out. But I want to factor. I've got 4 out of 51 times 3 out of 52 plus 48 out of 52. And then you add this together and you get 4 out of 51 times 51 out of 52. Those cancel and you get 4 out of 52. So if someone asks you, like, what's the probability of this thing happening like second or third in this chain of events, and you're pretending like you don't know what happened in the previous steps, it's always just kind of like you ignored everything that happened up until then to say, oh, it's the probability of however many things out of the total number that you would have started with, which is kind of a neat phenomenon. Okay, that's all I've got to say. I know I haven't posted a quiz for you guys yet. I will definitely post a quiz for you guys today. Again, it's purely optional. You do not have to do it. It definitely will not have any of the crazy Carlson questions on it. It'll be more double intervals and or probability stuff. And again, totally optional. You're welcome to do it. I'm happy to grade it. You don't have the time or don't want to do it, that's also fine. So I think that's, oh, let me give you guys the attendance one more time just to make sure we got it. And that's all I've got for today. Good seeing you guys. You're welcome.